Okay. All right, this should be recording. Hold on.
Yeah, recording.
Okay. All right. Good. Let's hope this works.
I'll
I set this up. Okay. I set this up like across from the whiteboard, so hopefully you'll be able to see. I'll try to write kind of small. All right. Okay. There's Lexi Black. Happy snow day.
Yeah.
All right, so it says recording. Hopefully it's recording. What I want to go through today, the two videos that I posted are about acid and base titrations, which is like the next topic in this chapter. But we're going to have strong acid, strong base titration. Lana, you're awake. Good job. Okay, get my coffee here. Hold on. I'll be honest, I was not really planning on this one. I kind of thought going to sleep that we wouldn't have a chance at it at all. All right, so strong acid, strong base titration. You guys did this in first year chemistry as well. It was one of the things we did towards the end of the acid-base unit, and we did one with hydrochloric acid and with sodium hydroxide. So this is going to be strong acid, strong base. I'm going to try to write on the board here. I don't know, again, how well. Hello, Grace. Yes, you erased that. I'll just try to stick with black, I guess, if we can. And we've mirrored this so that you'll be able to read it right. So the idea is maybe we'll try with the light too for a second. And we'll turn the front light switch down. You guys even see what I'm writing?
Yeah, we can see it.
Yeah.
Wait, it's behind me. Oh, over there. Okay.
Yeah, it's weird.
Yeah. Oh, shoot. Okay, how do I want that? And then if I, okay. So up here typically is your base. You're like, and down here is typically your acid. So this would be HCl. Doesn't have to be those two acids. They're the easiest to start with. Now, in a typical lab situation, you tend to know what the one in the burette is. Know the concentration. Sodium hydroxide, we could just say that it's 0.1 molar. So 0.1 molarity. And we just have that filled up, so we don't know how much volume we're going to add. Now, down in the flask, you have a certain amount of acid. Now, this you have actually like measured out. You know how much you have. So let's just say we have 25 milliliters down there. And the thing is we don't know that concentration. That's the concentration that is unsure. Kind of the whole point of doing a titration is because you have something that you want to know what it is. So we will say question molarity. So that's kind of the basic setup then of our titration. How's this going to work? Well, it's a strong acid and a strong base. And the other thing we will add, of course, is an indicator. You have to have an indicator in order to know when to stop. The indicator tells you when all of your base and all of your acid have reacted together. So there'll also be an indicator. indicator that we always use was phenolphthalein. Phenolphthalein indicators turn color at a certain pH. And phenolphthalein color a little above 7, almost to 8. It's kind of in that range. So when it's in an acid, it's clear. You don't see it at all. As you add base, when it's in a basic solution, once it's above pH 8, it turns pink. As you add a base for a little bit, it's still going to be clear. It's still going to be clear. It's still going to be clear. And then once you get to that point where a drop of base is now overloading it, that drop of base is now, let's see, the majority. You have to think of it like, first there's acid and there's base and they react together. There's acid, there's base, they reacted together. There's acid, there's base, they react. And then you're done with the acid. So now if I just put in base, all that's left is base, it's going to turn pink. And so it's just going to, you wanted to get it that pale pink color and not fuchsia, because if it's just that pale color, you know you're just at that point, past. But as soon as you start adding more base, it's just going to get really bright and pink and fuchsia, and you've gone way past the equivalence point. All right, now the mathematics behind it, the chemistry behind it. So we have a strong acid, strong base equation. So you have HCl plus NaOH. Strong acid, strong base. Okay, strong acid, strong base. So it's a simple double replacement. So you get your HCl and your water, and we would dissociate anything that is a strong acid, strong base. And a soluble salt. The NaCl is soluble. And the water is a molecular species, so that stays together. If those things will dissociate, then I'm going to end up having two spectators. What are they? Everybody's muted, except for Ben. Ben?
Spectators, hydrogen and Na.
Cl and Na.
Cl and Na, sorry.
Spectators. So the chlorine and the chlorine, Na and Na. So that leaves me with H positive, OH minus, to give me water. Okay, now, why do I have a straight arrow?
Because it's strong acid, strong base, they're going to fully
Strong acid,
dissociate.
strong base. Ann is not muted either, or Jack. You guys can pipe up. So strong acid, strong base, it's a straight arrow. All right, now because it's strong, straight, you have to do stoichiometry. Strong, straight, stoich. Okay. Strong, straight, stoich. So I'm going to put down the things I know like I used to with stoichiometry. So with my acid, I know I have 25 milliliters. I don't know my molarity. I don't know my moles. Let me see that, please. Yeah. And then with my base, I know that it's 0.1 molarity. I don't know moles. And then here's the thing about titration. Here's the thing about titration problems. They're going to give you random intervals throughout the titration. So they're going to say, let's say we add 5 milliliters. Let's just start with that. We're going to add 5 milliliters of base. And then we're going to stop, and I want to know my pH right now. So if I add 5 ml of my NaOH, again, I'm just making up these values different times throughout the titration. So I put that in here. So because it's stoichiometry, I have to do those moles down there, and I'll just do my molarity problem with my moles over liters. So I have 0.1 moles, my volume, we move it over 2 places, so 0.05 liters, which gives me 0.005 moles. Okay, 0.005 moles. So now I can do a mole ratio right over to the hydrogen. So since I know that it's 0.005 moles of hydroxide, it's a 1-to-1 ratio, so it will go right over to my hydrogen. And now I have what I need to solve for my molarity over there. So I have my molarity problem as moles over liters. So 0.005 divided by 0.025, and I get 0.2 molar. Now, this is only after I added 5 milliliters of base. I've only added 5 milliliters of base. This isn't at the equivalence point. This isn't anything. This is just at this time. And then to get pH, I have my hydrogen right there. I just have to negative log that guy right there. So 0.2, I negative log it. I get a really low pH, 0.70. So right now, my pH down here in the flask is 0.70. I only added 5 milliliters of base so far. Everybody okay with that so far? Okay. Yeah, hold on, I'm going to look at something. Yeah. All right. Now, something else that they could add, or they could ask you. They could ask you the pH at the equivalence point. The pH at the equivalence point. But I'm going to need to know a little bit more in order to do that. Because I don't, well, no, I take that back. I could do that right now, actually. Okay, so a titration of a strong acid, strong base, 2 species, the pH at the equivalence point is when all the moles of the acid and all the moles of the base have reacted together. They've all reacted together. So what pH would it be if all the moles here and all the moles here react and are down to 0? What would I have a beaker full of? Jack?
Not sure.
So all the acid's gone and all the base is gone. What did they both?
Wouldn't it just be salt water?
They just made water. A little bit of salt in there, but they just made water. What's the pH of pure water?
7.
7.
7. So I'm going to have a pH of 7. At equilibrium point, my pH is 7. Let's figure this out. I have okay. I don't know if we can do it from here. I know my molarity, I know my volume. pH of 7 would give me, okay, yeah. So a pH of 7, no, I don't think that'll work. Maybe, let's try it. 25 mils Leave this open for a second. Leave this open for a second. 0.1 molar. Leave that open. If I know my pH is 7, what does that tell me about my hydrogen? That's a key piece right now. See, you guys can see the red. If pH is 7, unlog that. Go 10 to the negative 7. One times 10 to the negative 7th, right? Is the molarity of my hydrogen, which would also be the molarity of my hydrogen at that point. So if I put that in right here, I can't do it like that because the volume's going to change. All right, got to change our problem a little bit. The volume is going to be affected, so it's not quite as easy as that. So let's just change our problem. I'm going to look at problem from your problem set on page 3. If you have the problem set. Otherwise, I will drop it as well. They just give you a little more information, but all of these relate back to what we just did. So, number 1, the whole page is basically a problem. It says that I have 50 milliliters of 0.75 nitric acid. So it's a strong acid. It's going to be very similar to this. But if you notice, they gave us the molarity also, 0.75, 50 milliliters. The nitrate's still going to be a spectator. It's being titrated with sodium hydroxide, very typical, and it's being titrated with 0.8 molar. A little bit stronger. So I still have my setup is the same. My equation is very, very similar. The very first question that they ask us is, when I'm at the equivalence point, how much base? When I'm at the equivalence point, how much base? So, again, if I set this up and I look at what I have, 50 milliliters, .75 molar, and then we'll leave the moles open. Don't know, 0.8 molar. Leave the moles open. Leave the milliliters open. Okay, now we're going to get somewhere. At equivalence point, the moles of acid equals the moles of base. So write that down somewhere. At equivalence point. Moles of acid equals moles of base. That is the key, so we have this right here. At the equivalence point, moles of acid equals moles of base. Okay. So now, knowing that, I can solve this side. I have my volume, I have my molarity, I can get my moles. So I can do this side right here. And I just use the molarity equation. molarity equation, 0.75 times my volume of 0.05, get 0.375 moles. Well, because I'm at equivalence, this is the spot where I'm at equivalence, that moles and that moles are equal. And now I know that those moles are equal, so that I have moles of base and molarity of base. I can solve for volume of base. And get my moles, my volume. So 0.0375 divided by 0.8 equals 0.468. We go 3 places, 1, 2, 3, 46.9 milliliters. That's the piece that I kind of messed with the first one. I added 46.9 milliliters of base, and at that point, the pink color stayed. I was at equivalence point. Now, in my flask, in the bottom of my flask, I have 96.9 milliliters total of liquid. 50 of it acid, and I added 46.9 of my base. Now I have a full almost 100 milliliters in there. Now, that's the first question, question A. What is the volume of base that had to be added at the equivalence point of the titration? And I did that because this is what I know at equivalence. Questions? Now, the idea here too, the idea with this one is that those 2 moles disappear. Those 2 moles completely reacted with each other. There's no extra acid, there's no extra base. They completely react. So now I have a beaker full of water, salt water, but water, and this is a pH of 7. So, something else to think about. Or maybe something else to add to this right here. At the equivalence point, second block is over. At the equivalence point, moles of acid equals the moles of base. A strong acid, strong base titration, at the equivalence point, the pH is 7. Like that's a for sure. It'll never be anything any different. So an SA, SB, pH equals 7. That is always, always, always true. pH is 7. All right, question. Okay, through letter C on that same problem. Still sticking with this. I'm going to move it up a little bit. It was 50 and 0.75. So he says, what is the pH when I haven't added any base at all? So all I have is this flask down here, HNO3. HNO3. What do I do to get the pH of an HNO3?
Would you have to find the moles of H? So we take the molarity times the liter amount. And
What's pH?
pH is H concentration or percent hydrogen.
What do I have? I have my
An acid. Yeah.
There you go. This one's super easy. You can
Okay.
think of it. Okay, so remember, a strong acid, 100% dissociation. So if it's 0.75, that means this is 0.75. It also means the nitrate's 0.75, but we don't care about the nitrate. Hydrogen is 0.75, so then you just pH that.
Oh,
And I got a really low number of 0.125. That's my answer.
yep.
Okay. So those first three, the A, the B, the C, they almost always ask that. They ask you about the equivalence point. They ask you what the pH would be there. Then they ask you, well, what is it at the beginning without anything added? Now, adding increments. They'll add a little bit of base, a little bit of base, a little bit of base. So let's look at D, part D. So part D, they're going to add 20 milliliters of base. Hello. I'm teaching AP Chem. Come say hi. Oh, yeah, we're doing video.
Ivan?
Hey.
Over there.
Those are students of ours.
Students or people? No.
Hey, Mr. Meeker.
Cool.
Yeah. They're all snug in their beds, I bet.
Good spot to be.
I know.
They had better shovel the driveways.
Who's already been out to shovel?
Me.
Ben raised his hand. Not Ben. That's not Ben. That's
Rock, good for you.
Yep.
You get ice cream tonight after dinner then.
Maybe.
Just if you want a day like today, right?
yeah.
Neat. That's a good one.
Thanks. All right. So 20 mils. So I just go back and I just like list out what I know. It's just back. These get to be kind of tedious because you're just going to do the same thing again and again. So I have, this is 50 mils. I'm going to put the liter amounts. So 0.05 liters, 0.02 liters, 0.8 molar, 0.75 molar, and I just look at my moles. So now I have both of those, so I can get both of those moles pretty quickly. 0.0375. Oh, 0.16. Okay, so now here's where the stoichiometry comes in. And normally we would set up a train track and we would figure it out. But this is easy. This is a 1-to-1 ratio. Which one of those two things is going to run out first?
The OH.
The OH. We have a limiting reactant. This goes back to limiting reactants. We have a limiting reactant in the OH. So that 0.06 is going to run out, and it's reacting with 0.06 of the acid. So it's eating up 0.016. It's eating up 0.016 of the acid. So I end up losing that amount. So the way that I write this, kind of a standard procedure, it sort of looks like the ice table. So I take 0.016 completely, and I take 0.016. Because again, I know that that is going to run out. That's going to be my LR, my limiting reactant. And then what do I have left over that one? O215. Okay, so that is then how much I have left over is 0.0215 moles. If you think about this, this had 50. I added 20, so now it has a new volume. So 50 and 20, I have a new volume of 70 now. And I have this many moles left over in 70 milliliters of volume. So from that, I can get my molarity. So this is how much is left, divided by my new volume of 70 milliliters. .07 liters. My molarity is 0.307. And that's the molarity of this hydrogen. Because all of my hydroxide is gone, my hydrogen is what's left. From that, pH it, negative log it. My pH went up. Now I am at a 0.513. So I start 0.25. Now I'm at a 0.513. It went up a little. Questions? Do you need to unmute yourself and ask?
So do we just do the exact same thing for the next 3 problems?
Yes. However, let's skip ahead. Let's do letter F. I want to do number F first. I'm going to shorten this a little bit for you because I think now that you kind of get, okay, we just use the molarity problem, we're going to shorten this a little bit. Okay, so for part F, they're telling us, okay, now we're going to add 60 milliliters of base. So I put 60. So the part is you already know how to do the molarity problem. So let's just do it. In the calculator, you have your volume, you have your molarity, get your moles. So 0.8. So I have 0.48 moles here. And that one's still the same. I forget it though. 0.375. So those are the same. You already had them. You might as well just do them separate or in the calculator. Now I plug them over here. I think it makes it really clear right here. It's not so busy. All you see is moles. So now that all I'm looking at is moles, who's going to run out? Who's going to be my limiting reactant?
Hydrogen.
Now it's the hydrogen. It's gone past my equivalence point, which I should have known that because I remember doing part A, which told me that my equivalence point was 46.9 mils. Now I added 60 mils. I'm past my equivalence point. So I should expect this anyway. So I know that my LR is going to run out, my limiting reactant. So this will be all gone. Which will leave me some leftover hydroxide. 0105. That's how much is left over. And then go back and think, okay, I had 50, now I added 60. So now I have 110. I have a whole lot in my flask. So I have to divide by my new volume. That's always one of the things that we forget is the new volume. Ooh, that gives me a molarity of 0.0955. What do I do with that? What is that the molarity of?
That's the OH
That's the
molarity.
So can I get pH from that?
No, but you can take POH and then 14 minus that.
So then you just have to know your chemistry. And you have to know, okay, that's just going to give me the OH. Negative log that, I get a POH of 102. Subtract from 14. A pH of 12.98. Which makes sense because it's mostly base. Or what's in there is base. So it should be high. What do you think?
Seems easy enough.
Okay. So again, I think just doing your molarity either in your head or in your calculator cleans that up for you. So you only have to deal with moles. Like you're only looking at moles. You don't have to deal with all that other stuff. You just look at moles, which really easily makes you see which one's going to run out. And then don't forget that afterwards you have to divide by the new volume in the flask because there'll be a total volume. So that is that. Questions that you have. Gosh, we have so much more to do.
Are there going to be problems where the acid and base are a 1-to-1 ratio?
Yes. So then you may have to do either a little training to figure out which one is the limiting reactant.
Okay.
I don't believe that AP would even do that to you though on a test because you are limited time. And I know that none of these problem set problems are that way, honestly. So it's possible, Jack, but I don't think you're actually going to see it. But you do have the skills to be able to do it. All right, let's see. Okay, so your homework for today was supposed to be page 2, number 1, 2, and 3, the whole front. Do you have any questions about that?
How do we do part D on number 3?
Okay. Calculate the pH of both buffers if 0.1 moles of HCl are added to each buffer. So, okay. Actually, having some of this in mind, we can do this a little bit easier. So, going back to what we have, I'll look through, which one do I want to do for you? Yeah, all right. I'll talk you through buffer A, so then you'll be able to do buffer B, okay? So buffer A, we had ammonia and ammonium chloride. So that means you have ammonia, weak, you have water, you have ammonium, you have Cl minus. So you have the weak base and then you have the salt. It says that we have 250 milliliters of the solution. milliliters. The molarity, we have 0.05 of ammonia. And then the ammonium is 0.15. Okay, now we're going to add our HCl. So we're adding that strong personality. So what you have to focus on is, again, who is that hydrogen going to react with?
NH3?
NH3, it's the best base. Ammonia is the best base. So over here we write straight arrow, strong hydrogen, straight arrow, joins together to make NH4 positive. Okay. Now, stoichiometry, strong, straight, stoic. Stoichiometry means to me that I need moles. I need to deal with moles. So the HCl that they're adding, they said they're adding 0.1 mole. Okay, 0.1 moles. We have that. We do need to get the moles of ammonia and we have to get the moles of ammonium because that's in there too. All of these things are what we have at the beginning before any reaction has happened. These are what we have. So volume, molarity. Again, I'm going to trust that you know how to do the molarity equation. So 0.05, and then you multiply by your volume. 0.125. And then the other one 0.0375. Okay, so with these two right here, reactant side only, do I have a limiting reactant? Who is going to run out first?
Would it be NH3?
The lower moles. The lower moles are going to run out first. So then this is where I say that I subtract all of it. I lose all of that. And it reacts with 1-to-1 ratio, so it reacts with this much over here. This ends up being 0. I don't have any moles of ammonia when this is all done. My acid will react with my ammonia so much that it all runs out, the ammonia runs out. I also then have to make some of the product, because this makes product. So I get an additional 0.125 over there. So 0.1 minus 0.0125, 0.875. And then that zero or 0.5. So what I have in my beaker right now, my acid came in and my acid completely reacted with all of my ammonia. The ammonia has now disappeared. It made some more ammonium, but I still have acid present. And I still have some ammonium present. Of those two choices, who dominates this beaker?
The hydrogen?
Hydrogen has to. It's the strong personality. So the hydrogen dominates. That means this is what I use to get my pH. So even though I did make some ammonium, it's not going to hold a candle to the hydrogen because the hydrogen is strong. So let's see, no volume change. Okay, good, no volume change. So I still have my 250 milliliters. And then I can get my molarity and I can get my pH from there. And that's that. Now I will tell you that the next buffer though, is a stronger buffer. And these two things switch, limiting reactants. And you end up losing all your H and you end up having some ammonia left over. So then here, your beaker will look like back to this at the end. How do you find the pH when your beaker looks like this?
Wouldn't you use the ammonium to find the POH and then subtract it from 14?
You have to set up an equilibrium. You can either start it with ammonium if you want to, or you can start it with base if you want to. But for the next part, you do this first, then you have to go back and you'll also do an ice table. So you'll have two things for the next part. Stoichiometry to figure out who's left over. That needs an ice table, equilibrium, to find the pH. It's a buffer. You're back to having a buffer again. And you could use Henderson-Hasselbalch if you want to. Question? All righty. What I want to do can we do one more problem? You guys have time for one more problem?
I have to sign off, but you guys can
Okay.
keep
Well,
going.
this is recording, so then I will post hopefully I'll be able to post the recording after.
All right, sounds good.
What?
Sounds good.
Okay. I do want to look at, and this is just to like revisit that thing I just talked about. I would like to look at number 4, letter D. Number 4, letter D. It just, we've basically been dealing with acids most of the time. This one is going to deal with a base. It just gives you a different look, but the overall idea is the same. So we'll do one more problem and then we'll call it good. Okay. This one, you got to look up above just to know what buffer you're dealing with. It's hydrofluoric acid and potassium fluoride. All right, so I have my HF. I have water. And I have potassium fluoride, which is a soluble salt. So I have some K positive and some F minus. So right now I have a buffer. And that buffer, it's 1 liter. That's good and easy. And it has, the HF is 0.6 molar. And the soluble salt is 1 molar. Okay, all right. And they gave us the Ka, so that's all right. So part D says, calculate the pH of the buffer if I add 500 milliliters of a 0.1 molar sodium hydroxide solution. So this time I'm adding NaOH, which is strong. So when it goes into the beaker, the Na and the OH, they split apart from each other. And I have now someone there that is strong. And the someone there that's strong is the hydroxide. So the hydroxide needs somebody to react with, and he finds the best acid available. The best acid available is the HF. So that is what I do first. That is the first thing I have to take care of, is that task right there. OH, HF, straight arrow, strong, straight, which means I'm going to do stoic. The hydroxide is ripping the hydrogen off of the F minus. And leaving us with that F minus. Okay, now I have to deal with moles because this is stoichiometry. Strong, straight, stoic. So I need moles. So I had 1 liter of 0.6 molar, so that's 0.6 moles. The hydroxide, now this one they messed us, they're going to mess with us a little bit. 0.1 molar, 500 milliliters. So 0.5 and 0.1 is 0.05. So 0.05 moles. Now I do have the salt in there. It was 1 liter and it was 1 molar. So 1 liter, 1 molar gives me 1 mole of it. And the water doesn't matter. Okay, between these two, I have a limiting reactant. I have somebody who's going to run out. Somebody who's going to run out, since it's a 1-to-1 ratio, is my hydroxide. So I will use up all of my hydroxide. Okay. So I use up all my hydroxide. That much reacts with that much. If it reacts with that much of the HF, it's going to create this much of F minus. So what does this do for me? What does this do? It takes care of all of this down to nothing. I have no more hydroxide. It ran out. It was my limiting reactant. It's used up. This loses O5. What does that leave me with? 5,5. That gains O5. So now my beaker has changed. All my hydroxide is now taken care of. All of my hydroxide has been reacted. It's taken care of. So what I have left are those two. So here's where I'm at that situation again. If those are the two things I have left, then what I have is a beaker full of buffer. And how do you get a pH of a beaker full of buffer? You have to do an equilibrium. So now I will turn around and do the equilibrium equation. HF is a weak acid. Weak needs water. It donates the hydrogen to the water. And I will set up my ice table. Now, stoichiometry needed moles. Ice tables need molarity. So I have to go back to molarity. Well, I know how much moles I have. I had a liter, but they added 500 milliliters of base. So that added quite a bit. But now I have a new volume of 1.5 liters. So it's just all these little wrinkles. So I have to take this, divide it by 1.5 liters. Divide this one, 1.5 liters. I have to divide them both like that. Now I have a molarity of 0.367. Don't care about water. Point 0.7. And 0. So now from here, I'm just going to let you guys, you can finish this because you can either use Henderson-Hasselbalch if you want to, because you have a buffer, or you can finish it with Ka and finish it that way. But then you just get your pH. So there's a lot of little parts to this. There's a lot of things to consider. The math itself is not anything we can't handle, but it can get confusing in like following the steps. What's going to happen first? What's going to happen next? And I'll tell you that students typically struggle with writing the equations, like just getting the equation down. So don't overthink. Really just think chemistry. Think what you know will happen. Chemistry. So that's all I got for you. That's your 60 minutes of snow day fun. Do you have any questions?
Yeah, I got a question.
Yeah.
Why did you use the ice table for this question, but not the one that we just did with the?
Hold on, let me put my volume up. Okay, say it again.
Why did we use the ice table for this question, but not for the one that we did before this?
Okay, so that's why I've tried to give you those clues. When something is strong, straight arrow, that means it happens to completion. So that means whatever reacts, reacts. And that's where we have to deal with moles and like create that product, or one of them's going to run out. Because you notice you end up with nothing of something. You have a limiting reactant. After, once you have what you have left over, those things are weak. And weak species establish equilibrium. So you'll never have nothing. Remember, that was the whole thing about equilibrium, is that you have some of everyone.
Okay.
Strong, straight, stoic goes to completion. Weak needs water, and then there's no W, but you got to use equilibrium.
Okay.
What else? This is probably, like, truly, this is the hardest. Like, this is the culmination of everything from these last 3 units. Equilibrium, acid spaces, and now buffers. Okay, so I know that Isabella got called into work. She's hopefully going to check this recording after. I don't know even where it records to. I know it's my computer somewhere, so hopefully I can not be technologically illiterate. But yes, enjoy the rest of your day. Get out and shovel for your moms and dads. I think my boys go home and shovel. And I'm going to end the meeting. If you have any questions, you can shoot me an email or throw it on Classroom. But otherwise, have a good day. Have a good night. See ya. And meeting for